model, which I will talk about, and then particle filters, which is kind of a Bayesian extension of a general path model, really. So if we have a degradation-based method, then we want to have a direct, ideally we would have something you could just directly go up and measure, such as the tread depth on your tire. In reality, we don't usually have that, and so that's where, in the first animation where you have the data and then you send it through your error correction routine and look at the residuals, we start to get useful information from the difference between how we expect to operate and how we're actually operating. And so here we've got everything's kind of chugging along, normal, 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 and then a fault occurs, and our degradation indicator starts to change up until when it crosses our failure threshold. So the general path model was originally developed for reliability analysis. It was developed in 1993 by Liu and Meeker, where they were looking at, we have all of this data from accelerated degradation testing instead of accelerated life testing, but if something fails before, if we stop our test before something fails, then we just kind of lose that information because it's a sensor unit, so all we do is say we know it would last that long. But since they were doing accelerated degradation testing and were collecting data about the system they were operating, they posited that you could take those measurements, extrapolate them out till failure, and call that your actual failure time, and then fit a distribution, and get a much, much different distribution than if you treat those as censored units. And so we took that idea and applied it to prognostics. It's basically just we have data, we're going to fit a function to it and extrapolate it out. And so here, if we have a bunch of, this was kind of their original data where they first proposed this, and so you have, these are crack length over cycles. And so when they crossed the failure threshold, then they said, okay, that's the failure time. So for all of these that actually cross our 1.8 inch failure threshold, those have a failure time. All of these that don't make it are censored. And so what they did was just applied a physical law, a crack propagation law, to say, okay, we know kind of how the crack was propagating. Can we just extrapolate that out to the failure time? The main assumptions that we're making here is that we have a unique degradation path for every item. So if you have two components that are nominally the same, you operate them exactly the same way, they're still going to have a slightly different failure path. And this is very easy to imagine because we have slight differences in manufacturing. That alone is going to give you slightly different responses to the exact same type of operation. And then there has to be some critical failure threshold. So some value at which you say, once my parameter crosses this value, my system has failed. And again, that's usually just a soft failure. So we have to be able to define something that will indicate system failure. Okay, and so the assumption that we have a unique path gives us the ability to do type 1 or type 3 prognostics based on the measurements that we're taking from our system. And we can kind of skip through some of this math, but the function here can basically be any kind of function. We can apply a neural network. Usually we use something much more simple like an ordinary least squares regression, which for many systems has been sufficient. For systems that are more complicated, you can go to neural networks, non-parametric models, some kind of splines, all of that. There's really no restriction on what the model that you fit your data to has to be. Basically, we're going to figure out what's a parametric model that we want to fit. So you have a parametric model, maybe it's quadratic, ax squared plus bx plus c, and you need to find the values of a, b, and c. So we're going to fit our parametric model to each one of these lines, quantify the mean and covariance to determine what the spread of our random parameters is, and you'll see why this is important in a second. So we want to know kind of, for each of those three parameters, what are the typical values for those parameters? And then once we have a model, when you start collecting new data, you know, okay, I want to fit a quadratic model to this because in the past that's what it's looked like. So you can fit a quadratic model, and then at the end of the time, the current time, you just extrapolate it down to failure, and whatever's left over between now and when it crosses your failure threshold is your remaining useful life. So it's very, very straightforward, but it actually works really well in practice. The one issue that we run into is that if you have a prognostics parameter that looks like this, so you've seen a whole bunch of things fail in the past, they've always looked like this, think, oh, it always looks kind of like a negative quadratic function. And then you just collect some new data, so you just have these red dots, which are the same in both, then which one of these would you think is more likely to be the true degradation path? So if we just take our data and fit a quadratic function to it, we're going to end up with this model on the left. If we know, though, that our function should be a negative quadratic and we force it to do that, then we'll end up with the model on the right. And so the model on the left doesn't make any sense in our system, right? That's not what we've seen happen in the past, and we can't, this is never going to cross our critical failure threshold. We're never going to get a remaining useful life out of that. But we can take into account the fact that we know something about how our system is operating and apply that with a Bayesian framework to just say, okay, that's why we were interested in kind of keeping track of, for our historic systems, what those parameters look like. So if we have a Bayesian framework, we have some data that we've collected. So these red observations, we have some data. We have a model for what that data should look like, which in this case is a quadratic function. We can use that to calculate the likelihood that we saw that data. So what's the probability of seeing all of those data points? Combine that with our prior belief of what our parameters should have looked like, and just with some Bayesian analysis, get a posterior distribution for what our parameters should be. So now we're combining our new data that we've just measured with our prior belief about how our prognostic parameter is going to go through time. And then as we get more data, then our posterior becomes our new prior. You combine that with new data and get a new posterior. And so just in traditional Bayesian statistics, you just keep updating that. And this is probably more than anybody's interested in, but we can do this in really easy ways. In an ordinary least squares sense, this is just the addition of a couple of extra matrices. So we have a covariance matrix here and here, so we take the inverse of the covariance matrix. And then as we have prior beliefs about our parameters, we just add that as a new data point to our matrix. So we have the data that we've collected at the top and our prior beliefs at the bottom. And then you just solve the pseudo-inverse equation. We can also, in a generalized least squares way, incorporate this information, accounting for the fact that there may be uncertainty in these measurement values here. But if we have prior beliefs about our regression coefficients, which we could get from our historical failure data, then we can just, if you can assume that these are multivariate normal, then you just have this very straightforward calculation to figure out what beta should be. If you can't assume they're multivariate normal, then it's a little bit more complicated of a calculation, but not too much. We've also, I didn't add it to this slide deck, but we've also looked at how to incorporate other types of information. So if we had, instead of having our prior beliefs about our parameters, maybe we just have our type 1 prognostic. And so we know on average the remaining useful life of our tires is 40,000 miles. We can incorporate that into this model as well to say that on average at time 40,000 miles, our condition indicator is at failure, at the critical failure threshold, and incorporate that type of information too. And so this actually gives you, if you use kind of your remaining useful life estimates from prior models, that gives you a lot more flexibility because you don't have to have these historic models. You don't have to have enough historic data to fit these prior beliefs about your parameters. But anyway. And so here, this is just for that, again, that same data. Now it's normalized 2% of lifetime. So as you get closer and closer to failure, your remaining useful life should become more accurate. That's a key feature of prognostics. If it's really wrong at the beginning of life, we don't really care because we've got we know that we have plenty of time to run before it actually needs to be fixed. And so we can deal with, we don't mind having large errors early in life as long as it gets better towards the end of life. And so without, if we don't have the Bayesian updating, so we're just fitting to the data, you can see that our errors tend to be much, much higher. eventually our Bayesian and our data-driven or strictly data methods converge to each other as we have lots and lots of data. Okay, so I kind of said this before, but our monitoring system residuals are our key components that we can put into our prognostics parameter. So if you're not able to directly measure something on your system that tells you what the condition of your system is, if we look at our residuals, then that kind of naturally tells you how far away from nominal operation you are. And so here we have basically 5 different engines just back to back, the residuals for 2 different sensors. And so one of them, it's kind of hard to see on the top one, but the red dots indicate where it failed. And so you can see here, like, this residual does not display a consistent trend. It doesn't have a consistent failure value, and it's not monotonic. Those are the 3 things that we're interested in for finding prognostics parameters. We want them to be monotonic because typically things don't fix themselves while they're operating. So if you had a condition indicator that was decreasing and all of a sudden it started increasing, that would indicate that your equipment started fixing itself. And that's typically not going to happen. There are a few systems that will, like batteries, but by and large, things don't fix themselves. They just keep getting worse. So we want something that is monotonic. We also want it to have kind of a tightly clustered failure value so that we can make a threshold to say when it crosses this value, then it's broken. And we all want them all to have the same sort of trends. So here they're all kind of negative quadratic functions. So we need them to have the same trends so that we can fit the same parametric model regardless of which specific engine it is. And so for this data set, we found 6 parameters, 6 residuals from our monitoring system that had this basic shape, combined them together kind of in the way that I showed at the beginning to get one single prognostics parameter. And then we get remaining useful life estimates that look something like this. And so here, again, when we have a long remaining useful life, so out here we don't really care if we aren't good. If our prognostic is bad, as long as it's not saying that you're about to fail so that you fix it before it should. If it's bad, that's not that big of a deal. As it gets closer and closer to failure, then we want to converge on the true value. So that's when it becomes much more important. And so here for this turbofan engine system, we were able to do, and some more recent results are certainly better than this. We kind of still use this data set for prototyping different algorithms just because it's very well understood now. People have been looking at it for the last 8 years. So it's well understood, everybody kind of knows what's going on. NASA's already come out and said, okay, here's what all of these measurements actually mean, so that it's not just a black box data challenge anymore. Again, so just to recap, for each type of prognostics, type 1, all you need is past failure data, reliability data. If you have reliability data, you can do prognostics. It's just not going to be great. Once you start operating your system and you kind of understand how it's going to operate and how that might affect the condition, then you can move to type 2 prognostics. And then finally, once you can measure something or infer something that tells you about the health of your system, then you can move to type 3 prognostics. With type 3 prognostics, you usually can't apply it until a fault actually starts, right? So once you have a fault and degradation starts building up, which fault could just mean normal wear and tear, or it could be like an actual fault. You think about your tires, like you're always wearing down your tires by driving, but if you run over a nail, that's a different type of fault. So, and so we can do life cycle prognostics where we start off with type 1 prognostics. You go and buy your tires, all you know is their reliability. And then as you start to operate your tires and you know kind of how you're going to be driving, are you driving long distances, are you driving off-road, are you driving in high slip conditions, then you can go to type 2 prognostics, and then finally, when you start measuring something about your tires, then you can move to type 3 prognostics. And so we have this life cycle of looking from when you initially purchase your equipment until it fails and you either fix it or put it back in, or remove it and replace it. You can kind of naturally transition between these 3 methods. And one of our graduate students in nuclear engineering is just wrapping up his dissertation work, looking at various ways that you can do this kind of life cycle transitioning across these prognostic types. So if anybody's interested, he's got a whole dissertation to read about it. And we've already kind of talked about this. So, the summary, what I was kind of trying to get across is that there is no one solution to prognostics. We have a whole toolbox full of different types of algorithms and models that we can apply based on what type of data we have available, how our system's being operated, how it's degrading over time, what we can measure that's related to its degradation. And we have lots of data-driven algorithms that exist, so you don't have to develop a high-fidelity first principles model that tracks the physics between, right now in nuclear power plants and probably in civil structures. They're trying to figure out how can they model from the changes in grain boundaries all the way until that turns into an actual incipient crack, and then that grows to a through-wall crack. How do you model that entire system? And just modeling it in a theoretical sense is hard enough, but then measuring something that'll tell you where you are across that chain is pretty difficult as well. And so we're trying to avoid having to have that kind of high fidelity first principles knowledge that we don't have for a lot of systems. And that, if you make a first principles model of your centrifugal pump, it is really for an ideal centrifugal pump. Your personal centrifugal pump will have some manufacturing defects in it. It'll have some weird little idiosyncrasies that are not going to show up in your first principles model, but do show up in your data because you're collecting the data straight off the pump. So, so you get kind of more accurate for your individual system when you look at these data-driven methods. And then the whole point is to, just calculating or estimating your remaining useful life in and of itself is not particularly useful or interesting. But then once we can use that information to either schedule our maintenance, so we can do truly condition-based maintenance, and kind of just-in-time condition-based maintenance, or changing the way that we're operating our system so that we can extend the lifetime to our convenient maintenance period. That's kind of where we're going with our prognostics and equipment assessment, is how to make decisions using this information. And it's just a couple of research opportunities for anybody who's thinking about this area. One of the big needs in prognostics is online performance metrics. So it's very easy to evaluate the performance of a monitoring model while it's operating, because you have the measurement and you have your prediction of the measurement. You can compare them and make a decision. Prognostics, we're naturally trying to predict something that's out into the future, and so we don't have ground truth. We don't know when it's going to fail. So while we're doing prognostics on a specific system, we can't evaluate the accuracy of our prognostic. Really all we can evaluate is the prediction uncertainty, which is useful and very important and tells us kind of how confident we should be in our remaining useful life estimate, but it doesn't necessarily give us the whole picture. And so if we're going to make decisions based on remaining useful life, we need to have a better understanding of how to characterize the performance while it's operating. We're looking at data analysis methods that can be applied during non-stationary operation. So for a lot of the vibration analysis, once you do a Fourier transform on your data, you're assuming that it's stationary data. And that may not be true. If you have something that's degrading, especially if it's degrading quickly, then it's not stationary data. We know that, but we're still applying a Fourier transform as if it were stationary data, so we're losing a lot of information. So people are looking at how do we do some data analysis during non-stationary operation, both for high-frequency vibration type data, as well as process data over an entire system. In the nuclear industry, we're looking for algorithms to mine information from large data. Probably everybody's heard of big data. That's kind of a big buzzword right now. And in some systems, we have big data relevant to prognostics. In nuclear and probably most industrial systems, you don't really have big data. So big data requires high velocity, high variability, or it's 3 V's, I can't remember the third one. So it's basically, do you have data coming in very, very quickly? Does it have, do you have a large volume? That's the other one. Where large volume usually means petabytes right now, 5 years from now, who knows what that'll mean. And then do you have lots of different types of data? So in nuclear power plants, mostly we have time series data. So we have process data, we might have frequency, but frequency spectrum across different time periods. So really it's time series data. We're starting to look at how we can pull in information from a computerized maintenance management system. So you have some like work orders and the results of doing maintenance. How do we combine that in there? But we're still not really getting into big data. However, a lot of the same data analytics would still apply here. It's just at a smaller scale, and so that much easier to do, really. And so we're looking at algorithms so that we can, instead of only using the process data, how do we combine lots of different types of data that may be coming from different places. When you start looking at maintenance data, then you have to look at natural language processing. If somebody's writing down, you know, I fixed the pump because it was leaking, or somebody else says, I fixed the pump because there was cavitation which caused a leak, or, you know, so the quality of the data is very dependent on the person who wrote what they did in the maintenance system. And so data mining algorithms for prognostics and health management are still kind of lacking in that area. People are starting to get into it, but there are a lot of opportunities there. And then finally, just methods to robustly and reliably integrate these results into your operations and maintenance planning, advanced control systems, maybe supervisory control systems, risk assessment, things like that. So how do we actually make decisions based on the information we're getting out of our PHM system? So these are, you know, across a variety of fields, these are kind of the big opportunities. They're also, especially if you're looking at passive components, so just large structures, then the big issue there is how do you measure something that's relevant to the condition of the structure. So if you think about a bridge or a pipe that's buried underground, how do we take a measurement on that pipe that tells us whether or not there's a crack initiating inside the pipe, right? How do you even get to the pipe? That's kind of the first problem, and then once you make a measurement, what do you need to measure? How do you evaluate that data? So for passive components, there's a whole first step that already kind of has existed for active components. So I think that's it. Yes. So if anybody has any questions, I'd be happy to try to answer them. I will give a plug for this summer. We're teaching a class in data-driven methods for prognostics in the nuclear engineering department, NE 575. So if anybody is interested, needs a class over the summer, think about signing up for that one.
Question? No question? I have a question. I noticed you use a lot of quadratic fit models. Can I do the log transform or square root to the linear?
Yeah, and so we have looked at, you know, so the methods that we used for this data, let me see if I can get back to it. We wanted to be able to apply just ordinarily squares. And so if you can do a transformation that will let you get back to ordinarily squares, you can still apply this very, very straightforward approach. If you can't, then you can just solve the regression problem a different way. But one of the primary reasons we were looking at something like a quadratic model is just because it's very straightforward to couch it this way is y equals x times b.
Okay. Well, another question, I also noticed you use a lot of censored data set. Is it left censored or right censored?
They are right censored.
So
because we usually start from beginning of life, but then if it hasn't failed yet, then that's right censored, right? We don't know when it's going to fail. There are some, and that's another problem, right? That we're assuming that we have the beginning of life data, which isn't always the case. If you have a system that's already, you walk into an existing plant, everything's already been running for a while, and you still want to start prognostics now. So now that's all left censored data, and so we have to account for the fact that we don't really know what happened from beginning of life to now, and just can we start now and move forward. So that's kind of another area people are looking at. Yeah.
And the last question is about your future research opportunity. For example, big data. So we already started use some tools like Hadoop or Hive or Spark or some software for the big data analysis in nuclear engineering, or we supposed to use it in the future?
So we, like I said, we don't necessarily have big data. The problem with nuclear specifically is that plants are not going to share their data.
Yes.
So especially if you say, I want to look at your data so that I can identify when something broke, they don't want to share their data for that reason. And so it's very difficult to get actual data from plants. And so a lot of it is simulated data or data from plants that have shut down. They're more willing to share their data. But again, it's not the volume of data that you would need to actually go to that. Something like Boeing, I think they use Hadoop and those kind of big data analytics because they have way more planes. Their planes fly, do much more interesting things, and so they have more something closer to big data. Tesla, I know somebody who works in manufacturing at Tesla, looking at how do they apply PHM to the manufacturing process, and they're looking at big data. So they've got a lot of different types of data coming in at once. It's not all just process data. Yeah.
That is on my question. Do you have any questions?
Yeah.
So you mentioned fitting regression parameters for maximum likelihood analysis. Do you have a physical example of what that might be in a given data set?
Right. So let me give you kind of a cop-out answer. So one of the nice things about data-driven methods is that it's not necessarily physics, right? We're looking at the data. We're saying what are the relationships with the data? What are the relationships between the data and the life of the system? And so we're not necessarily trying to say, okay, well, what's the number that I need to multiply by my wall pass frequency plus the number that I need to multiply by like my rotational speed. We're just looking at kind of a black box approach to doing the data analysis. And so the parameters that you fit won't necessarily have any kind of physical meaning. And when we look at like in this, let me see if I can. So here we're looking at, for this example, using monitoring system residuals. And so you can look back and say, okay, well, which residuals were useful and which ones went in there and try to extract some physical knowledge from that. But we don't usually go to that point because we're not trying to improve the design of the system. We're just trying to estimate how much longer it's going to run. Does that help at all?
The question?
I guess I have one.
Yeah.
How do you account for changes in the operation of the machine? Say they install a variable frequency drive, or they decide to run the machines faster and drive them into residence. Now you've got a fundamental shift in how it's being operated, so your historical data will kind of go by the wayside.
Right. Yeah,
Is there a good way that they're developing to? That's one of the problems I've seen in the last 10 years, and prognostics has made a lot of progress, tons of progress. But it's still one of the issues is that the reality and the prognostics are separated a little bit. It's kind of tail wagging the dog.
Right. Well, and we run into the same thing with just monitoring systems. Even before prognostics, if you fundamentally change the way you're going to operate, then any of your data-driven methods are not going to be applicable. The methods you've trained on your previous data. And so we've looked at ways that you can use like low to medium fidelity simulation models to simulate data, to then train a model, an initial model, and then as you start to collect some data, update that, update your algorithm to better match the data. But that's really the downfall of data-driven methods for anything is that you have to have data that bounds how you're operating. And so if you change the way you operate, then everything's going to look like an anomaly just because you've changed the way you operate. So we have kind of ways to try to get around that, and that's still something that people are working on. If you have a simulation of your system, how good does it have to be able to perform well, for your monitoring and prognostics models to perform well? And then, how quickly can you update it as you start to collect actual data from your actual system? Yeah, but yeah, so that is a big issue.
So there's still a lot of research to be done in that area.
Yes, absolutely. Anybody looking to go to graduate school, there's plenty of research.
No more question? Okay, it's all for today. See you next Monday, and Dr. Wuha Daya's vibration analysis. Okay, thank you.